Hello. In this video, we study relative extrema and critical points. Let's remind you about critical points. So, critical points are points where the first derivative equal to zero or the derivative does not exist. If you look at this picture, the first one right here, in this picture, the derivative does not exist at this point. Because you see the left endpoint, the left derivative and the right derivative are different, right? At this point, the graph is not smooth. So in this picture, in the second one, we have derivative equal to zero and the tangent line at this point is horizontal. So yes, in that case, the derivative equal to zero. And in the third situation, it's also, the derivative equal to zero when the tangent line is horizontal. And that is also critical point. Okay? So you can see these three examples about critical points, right? And if we pay attention on these three situations, actually the function attains minimum in here in some neighborhood of this point. You see some neighborhood right here. So if we just project on the x axis, so you have that neighborhood, right? So see that is minimum, right? Minimum in some neighborhood of the point. And in the second situation, yes, you see this point is the highest in some neighborhood. So in this case, that is the maximum. But again, this is not the maximum as global maximum we learned last time. This is just local maximum because that is maximum in some interval of that point. And in this situation, yes, you have the lowest one, right? Lowest point here, which is minimum, right? But again, that is local minimum. So when you look at critical points, you might have extrema, but local extrema. Okay, so I mentioned that is local extrema. Okay, the graph of function or the function might have local extrema at critical points. And it turns out that the function have local extrema only at critical points. Okay, so there's no other points, rather than critical points where the function may have local extrema. So based on this observation, let's move to definition of local extrema, or sometimes we say relative extrema. Okay, so if there is an open interval containing C on which Fc is maximum, then Fc is called a relative maximum. That's what we're seeing here in this picture, right? And if there is an open interval containing C on which Fc is minimum, then Fc is called a relative minimum or local minimum. Okay, so I write here relative minimum or local. So I just local in here and local in here. So what is the difference between local maximum minimum and global maximum and minimum? So we can consider the following pictures. Look at this. Okay, so suppose that we consider the function on a and b. Okay, this is b and this is x. You might have local maximum where at this point. You might have local maximum at this point. You have local minimum in here. Okay, let me write local max. That is also local max. That is local minimum. And this is also local minimum, right? But look at this. This function has two local maximum, but you know these local maximum are not global maximum, but this guy is global maximum. So I hope you still remember the instruction on how to find global maximum or minimum of a continuous function on some closed interval. First, we need to find all critical points, right? And then we compare function values at those critical points and at two endpoints. And then we have global maximum, you see? So a function might have several local maximum, but you know, no, but might not attain global maximum at those local maximum. And similar to the case of local minimum, right? So the function has two local minimum in here. And fortunately, the function attains a global maximum, a global minimum at that point. But you know, as local maximum, sometimes, you know, the function might not have, you know, global maximum at those where the function has local maximum, right? All right, so local maximum or local extrema are different, right? Are different from local global extrema. So that is the first thing we need to memorize. And the second thing is local extrema happens only at critical points. Okay, but not all critical points will be the point of local extrema. Don't forget that. You know, sometimes we don't have, okay? So let's consider the following example. You know, in this video, we consider local extrema very naively without, you know, consideration of increasing, decreasing property of the function, because I don't want to jump ahead with that, because I will teach you that technique, but not right now. Okay, so now we do very naive, you know, naive work about that. Let's consider the following function: y equal to 9 x squared minus 3 over x cubed. Okay, so we see that, you know, the domain of this function is the whole number line except one point, which is 0. And now we need to find critical points of this function. Okay, let me write here: find relative or sometimes local extrema. So we need to find in the domain, right? We need to find all points in the domain such that the derivative exists or equal to 0 or does not exist. So and this is why we need to find derivative, right? Always, we always need to find derivative. So in order to find derivative, I think I can break this function into two functions because I don't want to use quotient rule. So I have 9 over x derivative minus 3 over x cubed derivative, right? And I have 9 negative x squared because derivative of 1 over x is just x squared. For the second one, I think I mix 9 here, right? 3 times 9. So I have negative 27 x to negative 3 derivative. Then I have negative x over 9 over x squared minus 27 times negative 3 times x to negative 4. Okay, so I have negative 9 over x squared minus plus, because we have negative with minus, so I have 81, right, divided by x to the 4. Okay, so you see, yeah, if you want, you can write in this form: x to the 4 and then negative 9x squared plus 81. All right, the derivative does not exist at 0, but 0 is not in the domain, so we don't need to consider that. Okay, I can write that sentence in here: y prime does not exist at x equal to 0, but 0 is not in the domain. So 0 is not a critical point for the function. Okay, so that is the first thing. Second case is the derivative equal to 0. So you set negative x squared plus 81 equal to 0. From here, you can solve for the x. So you have x squared equal to 81 over 9, which is 9, right? Then x equal to plus minus 3. So the function has two critical points. Plus minus 3. And as we mentioned previously, the function may attain local minimum or local maximum only at critical points. So the function may attain local extrema only at plus or minus 3. Okay, so now we need to test which one is local minimum, which one is local maximum. Now let's consider the case when x equal to 3, okay? So you plug 3 into the function, you get f3 equal to 9, 3 squared minus 3 over 3 cubed. And that is 9 minus 3 over 3. So you have 2. That point is x equal to 3 and y equal to 2, okay? That is the first information. The second information, if you look at the function, that is 9 x squared minus 3 over x cubed. You might see that the function is not defined at 0. Right? The function is not defined as 0. And so, when x is less than 0, you have one branch of the graph. And when x greater than 0, you have another branch of the graph. So basically, I know exactly that, the graph of this function has two parts. The first one somewhere in here, the second one somewhere in here. Okay, that is not exact graph, right? But I just want to tell you, right? We have two parts in here, right? One is for x less than 0 and another one is for x greater than 0. And now we are considering x equal to 3, which is, belongs to this part. So we don't care about this. Actually, we don't care about this at all right now, okay? So let's care about the case when x greater than 0. All right, and I know that x equal to 3 is a critical point, right? X equal to 3 is a critical point. So I want to see if the function attains local minimum or maximum at this point. I may choose some point around 3 to test that. So I might choose like x equal to 2, right? I pick x equal to 2, I plug into the function f2 equal to 9 times 2 squared minus 3 over 8. So you get 9 over 8. This is less than 2. What does it mean? That means less than f of 3. You see, on this interval, the function has only one critical point. Only one critical point. And at that critical point, and in the neighborhood of that critical point, right, you might find at least one point, x equal to 2, such that the function value at 2 is less than the function value at that critical point. So what does it mean? What does it mean? That means that critical point should be local maximum. X equal to 3, or we say, the point 3, 2 is local maximum. Does that make sense? You see, you have graph, right? You might have some point like this or some point like this. Okay. Okay, let's do this, right? Let's choose one more point. Let's choose another point from the right of 3. So you have, let's say 4, right? You have f4 equal to 9. 4 squared minus 3 divided by 4 cubed. You get 9. Here you have 16, you have 13 divided by 64. This is also less than 2. So let's say this. You have 3, okay? So I have 3 in here, 2 in here, and 4 in here. The function value at 3 is 2. The function value at 2 is somewhere in here. The function value at 4 is somewhere in here. Right? So I have that. These are 3 points on the graph of the function. So how do you think? The function is continuous. So that means, the best way, the best way is like this. The graph of the function should look like that. That means at 2, the function attains local maximum. There's no way to get local minimum over there. Does that make sense? If at 2 you have local minimum, so at somewhere else you should have local maximum. And that is impossible because this point is the unique critical point on the interval from 0 to infinity. Does that make sense? Right now, we don't have any information about, increasing, decreasing. And I think that is the only way I can show you. X equal to 3 is local maximum. Okay? So similarly, you might guess at x equal to -3, the function attains local minimum. How do you think about that? I hope you can solve this problem yourself. If you have an answer, please let me know. Okay? If you are in my class, you get extra credit. Okay? So, I think we can finish this video right here. In the next video, when we study increasing, decreasing property, we will talk more about the first derivative and how to use the first derivative to classify local extrema. All right? Hope that you enjoyed the video and see you in the next video. Bye-bye.